Hi, good afternoon or good morning. My name is Jan Thomas. I go by JT. I'm Senior Director at Change Healthcare. So I'm going to quickly go over some of the work we are doing at Change. Also talk about the AI and NLP work at Change Healthcare as well. Let me start off with a fun fact here. I'm not sure how many people are familiar with this graphic. This is called as the first 5,000 days. It is actually some graphic called as NFT or non-fungible token. It was sold for almost $70 million. It is a collage of 500 days of an artist called as Beepley. So he has done a collage every day and he has posted it and created this massive 350 GB image. And it was bought by a Singapore-based person to host it, put it in his virtual world. So I just want to point that out. This has happened. I'll let you guys promise you how this all gets together as well. Yeah, this is a pretty fantastic collage. So let me dive into what Change does. So we are the largest administrative healthcare network in the country, and we connect the payers, hospitals, and providers, the hospitals and dental clinics and laboratories with the payers, who are the insurance companies, so that we can process the claims. So our mission is to transform the healthcare by reducing waste, and as you probably know, up to the estimate is up to 30% of the U.S. healthcare spending is wasted, representing an almost $1 trillion opportunity for all of us. And our goal is to use AI to transform this industry, AI and ML, especially the NLP part of it, to transform the industry as well. In applying large-scale algorithms to remove the feedback loop, such that we can process the claims faster without too many of manual process. So that's where my team comes in. So we use a complete AI first approach to automate some of these processes we have in Change Healthcare, as well as faster process the claims using AI as well. So our vision is to sort of so now I can relate to that NFT image. The reason I put that up is I was using the Facebook, and suddenly this information was there. So if you look at it, the Facebook and YouTube, they are using all sort of data. In fact, I never used Facebook at all that much, but they pretty much know exactly what I'm doing, what my interests are. The reason being, they're getting data from everywhere else. My activities in YouTube, my search histories, my location histories, my browser history, my telecommunication history, which websites I'm visiting from my home. So they get a clear end-to-end picture of everything I'm doing. By using all sort of data, they then flow that through their algorithm. Algorithms they have built, which then which then creates insights which are stored in the knowledge graph. And then essentially the Facebook is sort of built using that, or Facebook or even YouTube or any of the modern applications, consumer-based applications are built using on top of the knowledge graph. So that's why they have changed the paradigm of how we use the application. Instead of user-based, where traditionally our enterprise application, we had to keep typing a lot of information or asking for queries, pulling the reports, to sort of data-driven application where the information is given to the user. So most of the, almost like if you used Facebook or any of the modern social media apps, you are given the information. They're pushing you all sort of information, which is of extreme interest to you, like, so that's how I got the information. Our vision is to get the same experience in enterprise, or healthcare. So we have a data cloud which has data from all our application suite of applications, and then we run it through a model, a number of NLP models and other models we have built, which generates these insights, which is stored in the knowledge graph, which has a clear, intimate understanding of our customers, how they, what are the information they want, and, like, how is it all related, how are all the data related, and then we sort of build applications. Our vision is to build applications on top of it, which moves from the user-centric to data-centric application. So that is our vision, and we're using NLP to power some of these models as well. In addition to that, we are also using a service-oriented approach to AI or NLP, where we break the key AI lifecycle into a number of services, and then we sort of wire it together to build an ML application, which can be reused again and again. Like, in this case, you can see, using AI, platform, we have built an OCR service, which can, like, sort of using a command line, like, you can create the OCR service, and then after you extract the data from the PDF, you then train it using another command, in this case, and then wire it up, those OCR and your training service to train your model very elegantly using 3 lines of code. Like I mentioned, we have a number of services which cater to the AI lifecycle. We have a model training service, labeling service, workflow service, data processing service, inference services, both in batch and real-time inferences. And then we built these machine learning applications using these services. So you can easily, like, compose a complex machine learning application by just using out-of-the-box services at scale. So that's the way we develop our application. So let me talk about one use case, how we use NLP at Change. So I'm going to talk about clinical NLI, which is natural language inference model to extract. Our goal is to extract ICD code from patient charts. So we get patient records from the hospitals in PDF formats. These are all in PDF formats, and also from laboratories, the reports and other things. We get it into Change Healthcare using various means. These all come in the PDF charts, and then to Change Healthcare. And then what we do is we convert, using OCR, these PDFs to text, and then we use clinical NLI models. And then we'll talk in detail about the clinical NLI model in the next few slides as well. And then we have a complex set of services, workflow services, which is basically our analyst, or we have a set of coders who review those ICD codes, which comes out of the clinical NLI model. And then we essentially convert ICD code into something called as HCC, or risk assessment factor of a patient. So that's where we get this dollar amount, so that's the primary job of this particular application, is to identify the risk of a patient, to ensure. Essentially, you get the patient data, you pass it through the AI model. The AI model predicts a set of ICD code, and the coder reviews it, and then either corrects it or manually provide the feedback back to the application. And then a group of ICD code is called as a HCC code. And using computation, we can then compute the, once the HCC code is identified, we can then, compute the RAF, risk assessment factor, which is what the primary goal of this application is. So coming back to the clinical NLI, so this is a typical data set I have put in, where there's in the chart, the patient records, like, you can have a chart like the doctor would have written, like, the patient has type 2, diabetes without complication. And then in this case, we have a label, hey, this statement says there's a hypothesis this ICD code matches this. And another statement I've given is example is patient has diabetes, and then in this case again, like, the same ICD code matches, or the patient. A simple another example could be the patient has high blood pressure, and in this case also matches to the same ICD code. So there are different terminology for the same diseases. There is the user patient, the doctor may use any of these things, and it all have to map to the same ICD code. So that's the challenge here. And the patient record could contain up to 10,000 ICD code. For example, that's the number of ICD code which has got the ontologies for the entire diseases catalog. Could be up to 20,000. So we had to map all these things to that, to one of these ICD code. So the way we have approached this NLI problem is, we identified there's only top 10 ICD codes which map to the, to 40% of our patient, population. And then our models are trained to sort of catch those low-hanging fruit, the 10 ICD codes, extract that with high precision, and hence, we can then assess the risk assessment of the patient easily. So that's a hypothesis we have. So the options we explored, which I'm going to talk in detail, two other options we have built in-house, which is the clinical BERT, which is fine-tuned with the UMLS knowledge graph. I'll talk about it in detail. So it is basically there's different ontology. The idea is to map, to one of those, standard, map those different, domain-specific words into a certain, into certain mapping, and then the knowledge graph has that information. The other one is to use BioBERT with CRF, which is the which uses this. It's a sequential model as well. The third option we also explored, out of the box option, is using AWS Medical Comprehend, which worked very well. It comes with out of the box. You feed in a chart, and then it basically identifies all the ICD code, and all we need to do is extract out the HCC code, then do the RAF factor. So we evaluated that. That worked well. Because our prior, there is a number of processes we had to do prior and after to that. We developed our own in-house model, which has a similar performance, or we hope to have better performance in future as well. So the first, so you can read about the AWS Comprehend on your own. There's plenty of material, so I'm not going to go into that. The option one, AWS Medical Comprehend, but I'm going to go a little bit deeper into this. The clinical NLI with clinical BERT with UMLS option. So in this case, you can see here, it's a deep neural network trained with by data annotated with ICD labels. So the model used is clinical BERT plus the unified medical language systems. So what does your UMLS provide? So UMLS is a contextually embedding model that integrates domain-specific domain knowledge during the pre-training process using a tool called as MetaMap. So UMLS is a compendium of many biomedical vocabulary with associated information such as synonyms, hierarchical groupings. It allows for connections of words that represent the same underlying concept. For example, like the word lungs and pulmonary share the same similar meaning and then can be mapped to the same concept of unique identifier CUI. So essentially, it maps different similar synonyms to a common unique identifier, like the diabetes and blood pressure. All of these things are synonyms. You map it to some some unique identifier, and then use that to fine tune your model. So in this case, you can see here the advantage of clinical BERT. In addition, we chose clinical BERT, which sits on top of the Bio+, and it uses the MIC2 dataset, which is labeled by clinicians. So it has got clinical notes and discharge summary documentations, embeddings in addition to the PubMed and other scientific documents available in the Bio+. So we chose the clinical BERT because of our domain specific. And the only innovation we added is we further fine-tuned that with UMLS, which is the unified medical language ontology. So you get this, then it predicts the ICD code. So that's the whole idea behind this. And this worked out well for us in this case, in this particular example. Going to the next option, we also evaluated a sequence classification model. So in this case, the whole idea is so we want to look at the statements, look at the future words, the next set of words to identify, extract the NER, and then essentially look at the entire word and entire sentence, and then identify the NER, and then we further do the mapping. So in this example, I given you have a statement like this patient has diabetes mellitus, and then the Bio+, we chose Bio+, because it has got all the biomedical text. It is trained using PubMed and other scientific journals, so it contains all the details of details of those vocabularies as well. So it is trained on top of BERT, and it provides embedding. And then our job is to then fine tune using our data set, and then apply a classification CRF, which is a conditional random field model. So the idea behind that is the idea is to use the past and the future of a given time. And that's why we chose the bidirectional LSTM. So leveraging the bidirectional LSTM, we can efficiently make use of the past features as well as future features for a specific time frame. So we trained the LSTM network using backpropagation through time and forward and backward passes over unfolded network over time as well. So in addition, the reason conditional random field is important, it takes a similar approach as the bidirectional LSTM. So at a very macro level, there are two ways to use the neighbor. So in this case, it uses the neighboring surrounding. It looks at surrounding tags and words to infer what the user has spoken, or the sentence, to identify the named entities in this case. It also looks at not just each individual word. It looks at the entire sentence. So there are multiple ways to do that. One is to use the probabilistic way of doing things. Basically, we find out what are the nearby words to myself, and then use the probability to identify using maximum entropy Markov models, or maximum entropy classifiers. So those are a few ideas you could use. But this approach of using the entire, but that one still uses the things in isolation. It's not looking at the sentence level, information. So that's why we chose CRF, which is proven in the industry, a combination of bidirectional LSTM and CRF is much more powerful for sequence classification model. And it provided us better accuracy than the other options. In this case, as you can see, it basically classifies the sentence as a result diabetes mellitus, and then you can do further ICD mapping using another model to identify the ICDs in this case. In conclusion, so this is a sort of a quick performance summary. So like we mentioned, we have identified the top 10. Our models are targeted for the top 10 ICD code. You can see here we're able to sort of accurately predict those. I have put the lists option 3 and option 2. Option 2 in this case is the clinical BERT plus UMLS. So we're still working on, this is all still work in progress. This is just a snapshot of work in time at the level of our thought process as we speak. To summarize, basically what in Change Healthcare, we've taken a platform-centric approach to NLP. We use a number of services which does the core activities for NLP applications, such as training a model, labeling a model. So we have a number of services or inference. So you just, to build an NLP application, you bring in these services rapidly, and all these, so we also went through a use case. We deep dived into one of those use cases where to explore how we are thinking of NLP in the domain of charts, patient charts. So thank you for your time, and it's a pleasure talking to you all. If you need any additional information, feel free to reach out to me as well. Thank you so much.